we're now going to do Dijkstra's algorithm, a single source algorithm on a directed acyclic graph. No, I'm sorry, it's allowed to be cyclic, but no edge can have negative weight. That's a rule. All right, now, the basic idea is that we have fully processed nodes where we have looked at all of the top neighbors. We have partially processed nodes which we have visited, but not fully processed, and we have unprocessed nodes where we have not even visited. So initially, we have visited S. So S is partially processed and there are no fully processed nodes yet. Now, initially, we're going to put a cost as a green number in each one of these nodes, and the initial cost for S is 0, and the back pointer is undefined because, of course, the cheapest path to S itself is a trivial path. All right, now, we're going to fully process S, and in order to fully process S, we need to look at all its out neighbors. We'll do that in alphabetical order because, you know, why not? And the first thing we do is we notice that we can get to A at a cost of 4, we can get to E at a cost of 2, and we can get to G at a cost of 8. And the back pointers, first we put in the values. For G we get 8, for E we get 2, and for A we get 4, and the back pointer for each of those is S. All right, now, the partially processed nodes are stored in an updatable min queue. Since it's a min queue, we will fully process the element which has the minimum cost, and that is E. So E will be fully processed in the next iteration, which means we have to look at all its out edges. Now the out edges of E are D and F. So 2 plus 3 is 5, and 2 plus 8 is 10. So those will become the cost values for D and F. And the back pointer for each of them is E. So far, nothing particularly strange has happened. And now we have 2 fully processed nodes and 1, 2, 3, 4 partially processed nodes, and those are stored in an updatable min heap. All right, now we look at the lowest value of cost, and what we do is we delete that from the heap and fully process it. So A is now to be fully processed, which means we must look at its out edges. Now the out edges of A are B and G. So for B, that was an unprocessed node, so we get the value 6, and the back pointer A. And for G, we get the value 4 plus 3 is 7, which however is an improvement over the previous value. And so this is now 7, and the back pointer is A. All right, now let me draw the back pointers in the picture here. We have back pointers here, 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 and we did have a back pointer here, but we don't anymore. This 8 has been deleted and has been replaced by 7, and there was a back pointer previously from G to S, but that's now been deleted and replaced by the back pointer from G to A. All right. Now, at this point, A has been fully processed, and the partially processed nodes include B, D, F, and G. And the question I ask is, what has the lowest cost value among those? And the answer is D. The value is 5, which is the smallest, and so it becomes the next fully processed node. And we look at its out edges. What are they? G, C, and F. All right, we will look first at C because that's the simplest one. 5 plus 6 is 11, and we get a back pointer of, from C, the back pointer is to D. So that means that we have 11 and the back pointer to D there. All right, now the other out neighbors of D are already partially processed. And so we need to look at those. If we look at the out neighbor F, 5 plus 1 is 6, which is better than 10. Now what that means is that F has a new back pointer. It points to D now. And so we have to update this to 6, and this is updated to D, the new back pointer. All right, now we're not done because D also has an out neighbor G. 5 plus 1 is 6, which is an improvement over 7. So this becomes 6, and the back pointer of G is once again altered. It's no longer A, but is now D. And so we have the value 6 here, and the back pointer goes to D. All right, now we have fully processed D and A, and what is the cheapest remaining partially processed node? Well, we have 3 partially processed nodes, B, G, and C. Of these, 2 have equal cost, and we can process those in either order. We'll process G first. Now, when we process G, we look at its out neighbors. It only has one out neighbor, which is B. 6 plus 4 is 10, which is greater than what we already have. So no changes occur, and now we are done. We have now fully processed G. Our next choice is B. B has, again, one out neighbor, and that's C. 6 plus 8 is 14, which is greater than 11, which means we make no change there. And so now B has been fully processed. All right, now that means that the only remaining node that is not fully processed is C. So we have to do C next. C has only one out neighbor, which is G. 11 plus 2 is 13, which is larger than what it already has of 6. We are now done. The green numbers here are the cost values, and the red arrows are the back pointers. If I want to know the cheapest route from S to G, I start at G, follow the back pointers, and read these backwards. S, E, D, G is the cheapest path. And the same is done for all the other nodes. Now, one way to explain this, another way, is we divide the nodes into 3 classes. Those that are unprocessed, which have not been visited, partially processed, they've been visited, but their out neighbors have not always been visited, and fully processed means that they've been visited and their out neighbors have been visited. And nodes move from unprocessed to partially processed, then to fully processed. Initially, the start node is S is partially processed, and all other nodes are unprocessed, and no node is fully processed. And you notice we process these, we moved these from partially processed to fully processed in this order when we did it. And the green numbers were the values which we had when we when we visit a node for the first time. Now the green numbers are updatable. This is why we call this an updatable min queue. Whenever we want to fully process a node, we always pick the one that has the smallest value, smallest cost value. But the cost value can change inside the min queue, so we call it updatable.